So really, I only signed up for one talk,
Uh-huh.
and the other one was supposed to be a poster. There is no poster session at this meeting, so so that, and yeah, and then this one was George Kazanov's invited talk, and apparently I did something to make sure that he is not here. So he. And he asked me to give this talk because I was his PhD student that worked on this back 20 years ago now, doing superthermal electron modeling in the coupled ionosphere-magnetosphere system and looking how it influences the thermal plasma. So this is his talk. And if it were mine, I probably would have swapped out half of this for Mars and Venus photoelectrons and precipitating solar wind electrons, because they're fun to compare the electrons from here and there. But so my main punchline here, though, is that at least in the Earth system, superthermal electrons are ubiquitous, and they're very efficient at transferring energy to the thermal plasma and at interacting, at least in terms of electric fields, with the thermal plasma and helping to drive ionospheric outflow. So, quick summary of where they come from. There's something over here. This is a pen, not a laser pointer, isn't it? It is? All right, okay. It's also a pen, though. Yeah, how about that? Okay, so two main sources is that either a photon or some other energetic particle smacks into a neutral and pops off the electron. So that's the basic gist of superthermal electrons, and that when they pop off of the neutral, they come off with some energy in the tens of eV, maybe up to hundreds of eV, depending on how hard they were smacked in order to come out of there. But that's basically the two main processes that form it. And then they can have a wide range of interactions once they're launched into space. And so the big part of this is that a photoelectron, or a superthermal electron at, say, 25 eV, it's moving fast. And so, what is that speed? A 25 eV electron is moving at something like 2,500 to 3,000, if I'm doing the math right, kilometers per second. So essentially 2 seconds per Earth radii or so. And so these particles are very quickly, if they don't collide, if they aren't in a collisional region, they'll very quickly escape from wherever they were produced and have non-local effects. So they play a significant role not only in heating the local thermal plasma, but also moving that heat flux around and then becoming scattered against even just a small scattering rate is enough to cause it to go into the geomagnetic trap, and there they can last for hours and hang around all the way to the night side and form quite a energy source for the night side. And in the high latitude region, we've already heard about how they help pull the high latitude ionosphere out and contribute to polar wind outflow. Okay, so this is his schematic. I'm just going to step through superthermal electrons. Once they've escaped and they're in the plasmasphere, they can heat the plasmasphere, which then changes interactions with ring current and radiation belts. Shasha just mentioned interaction of ring current heating thermal plasma, so does the superthermal electrons as well. That can also influence magnetospheric convection, and continuing on, superthermal outflow can drive ionospheric outflow, which can then feed back on convection and magnetic field, and as well as interacting locally with the ionosphere and atmosphere to heat it. So these purple lines out here are where the superthermal electrons are interacting with directly, but indirectly having a much broader range of where the influence happens. Okay, so like I just said, they fly out really fast, and they produced, let's say that they're produced down here as secondary electrons from impact or photoelectrons. Then they might deposit their energy locally, or they might come up the field line and zip all the way to the other side. This picture over here is a map of along the field line in the vertical direction, and then in the x-axis, cosine of the pitch angle. So as the particles move along the magnetic field line, they'll get focused down. And because the source is at the strong magnetic field region, this isn't a loss cone, the way that we normally talk about with a magnetospheric population. It's a source cone, because that's where they're coming from, is at these strong B field regions. And so even a small scattering rate is enough anywhere along here to populate them, and they'll move in these elliptical patterns on this picture here, and they can last there for a long time, slowly being scattered back and forth within pitch angle space there, and slowly degrading in energy, and eventually jumping back into here and going into the ionosphere. So a useful thing to do is, if the systematic motion is in this elliptical motion in position along the field line and pitch angle, then a standard thing that we would do is convert it to some other more convenient coordinate system, in this case equatorial pitch angle, and define that everywhere as the pitch angle grid. So now you have particles starting in the ionosphere given some equatorial pitch angle that's associated with, and now they move in straight lines. And so numerically, this is a far better solution. We get rid of that systematic error that might arise by chopping this grid up into a Cartesian grid. Now we can chop this into a Cartesian grid, and everything is much more natural. As they move along in one particular direction, if they're produced in this ionosphere and they move along here and they're slowly being scattered, then if they hit this edge, they just simply jump over and move down. And so we jump across this region of no solution in equatorial pitch angle space. So only at the equator do you have the full equatorial, the full pitch angle from -1 to 1 in cosine. And that makes the solution much easier. And the point there as well is that even small amounts of scattering along these motions, through the magnetospheric portion of it, where you normally think of it as being collisionless, but even a small scatter, you don't need too much of a delta mu in order to trap those particles, because this gets very small, especially as you go out and out in L shell. L of 4, L of 6, the source cone is only a few degrees, like 3 degrees wide at geosynchronous orbit. So yeah, you don't need much of a scattering rate along that very long path of a geosynchronous closed field line in order to trap. So you actually can trap many of the photoelectrons along the very first path through the ionosphere, or through the magnetosphere from conjugate to conjugate ionosphere. This is a comparison that George did against fast data, showing several different, the dots are the fast data, and then using 2 different manifestations of the thermal plasma density along the field line in order to show how much scattering along the field line is necessary to match those results. And so you can play with this and get different levels of trapping within the field line, and therefore try and understand, based on these observation data model comparisons, how much material is out along that field line. Okay, so another concept that George likes to talk about is something called plasmaspheric transparency. So along these closed field lines, you have some amount of material coming out the topside ionosphere, and another amount entering the conjugate ionosphere. And if you just divide what's entering ionosphere number 2 by what was leaving ionosphere number 1, that isn't unity. In fact, it's usually lower than unity, but actually for some energies along there, it can actually be more than unity, as particles are, especially at the very low energy. that is. So particles are leaving, they get scattered, they bounce back and forth, they slowly lose energy, they're slowly scattered back into the source cone, now a loss cone for them, and they precipitate down. So at the lowest energies of just a few eV, you can actually have transparencies greater than 1 in this steady state situation. And at the higher ends, you can have transparencies that are essentially 1 as the particles are moving through, and somewhere in between you can get rather dramatic decreases in the amount of flux moving through from one ionosphere to the other. So that's this formula right here. It's just taking that one over the other to calculate a transparency. He got, how do we do that in the code? We can come up with different values of this transparency based on how you apply the scattering rates inside the code. So this T3 down here is if we turn on the photoelectron source in one ionosphere, not in the other. So all they're going to do is precipitate down, but then they can also scatter and come back out, right? So the full transparency that we were just talking about, that's this thing up here. You actually have production in one ionosphere, scattering, you lose some along the way, you gain some along the way as it's moving through the magnetosphere. It goes into the other atmosphere, it scatters there, it might be lost in energy, but there's some albedo of the particles backscattering out of the conjugate ionosphere. Now they're moving back through the plasmasphere again. Some are scattered, some are gained again. Goes into the first ionosphere. Again, there's an albedo. So you have albedos from both, from A1 and A2 from the two ionospheres, as well as transparencies as it's passing back and forth, as well as this beta amount, the amount that's returned from the trap zone. And so how do you determine these alphas and betas and various albedos in here? He came up with a method of how to do that based on the calculation by turning off and on various amounts of scattering, whether you're scattering stuff into the trap zone and allowing it to come back or not allowing it to come back, turning off and on the illumination, allowing it to return from the conjugate ionosphere. And you can get a handle on the contribution of each of those terms to the amount of material bouncing around inside between the conjugate ionospheres. So you can do these calculate. This is a spectrum along the energy, and I'll show some results where we're integrating across these energies and dividing one flux by another flux across all these energies to get a total transparency of the photoelectrons coming out of one ionosphere and where they end up. So if you have a high flux tube content of thermal plasma that you're scattering against, Coulomb collisionally scattering against during that plasmaspheric passage, he has 3 different runs here that he's showing. One is where you have transparency, where the particles just move and go. So this is a normalized flux level, and the transparency value is the ratio of the hashed amount to the full column in there. So this right here is a ratio of the transparency of about 0.6 across all energies. This first column then is a transparency of 1. We're just letting stuff go and how much hits without any scattering at all. So that just shows you how much was coming out of the ionosphere to begin with. But then if you turn on scattering but not the return, you get this blue curve, quite a bit less actually. So you are scattering quite a bit of your photoelectrons into the trap zone, even just on a single pass. And the yellow curve is when you turn everything back on, so now you're allowing the particles to come back and reflect from the conjugate ionosphere, and you return some of those particles. In fact, you return a lot of this, so your transparency goes up quite a bit as you turn on those other processes. If we change the density along the path, so this is different L shells, and you can see how that transparency changes quite a bit out to L of 6 compared to L of 2, just from the much longer path length and the much smaller source cone, changing that configuration. If you deplete the flux tube, though, so now we're outside the plasmasphere, we're on a plasma trough, field line, transparency is quite a bit different. Most of the photoelectrons make it through the magnetospheric passage and impact the far flux. And if we turn off the conjugate ionosphere, so all we've done is just turned off the source in the other side, amazingly small numbers. So now we have material bouncing back and forth, but not much is coming back. So most of the material that makes it through the fly-through is lost in the conjugate ionosphere and doesn't return. So all these values, you just saw that all the columns drop by a factor of 2 here from one to the other or so. Okay, moving on to higher latitudes, talking about precipitation of electrons into the ionosphere and the production of secondaries. We've heard a little bit about this already from Kitamura and Kepler in the last couple days. So this is a calculation of applying 2 different types of primary spectrum, whether it's a sharp Gaussian distribution or a broader Maxwellian distribution, watching it go down into applying it at some high altitude region, maybe 1,000 kilometers or so, and watching it come down through the atmosphere and produce secondaries along the way. And so this down here are the secondaries produced by this primary production, and by this primary source of superthermal electrons coming down. You can see there's quite a difference depending on how this same energy flux coming in, but arranged differently in terms of its energy spectrum. And you get a very different amount of photoelectrons here. So there's just a ratio of this divided by this gives you this over here. And here's the 1 mark. If the 2 were even, it would be here. So you can see quite a big difference where it's, depending on altitude, depending on how you put in the particles at the top, you get a very different distribution at low altitudes in terms of the secondaries and where the heating might actually be taking place. I think that's the point of that slide. And this is just additional calculations of how much of those secondaries produced are coming back out of the system based on different types of energy inputs from the top. Okay. This is again looking at that total escaping photoelectron and now doing it on a closed field line. And George did simulations across an entire closed field line going all the way out into the plasma sheet and back around. And how much of those photoelectrons return. And you can again do divisions of these columns here, and quite a bit of the precipitating energy escapes back to the magnetosphere in the form of secondaries coming down, and quite a bit of those secondaries actually ricochet off the far ionosphere and come back, at least in these simulations. So these return superthermal electrons, quite a few come back. And finally, he did calculations in the polar wind region and adding some small percentage of photoelectrons on top of thermal electrons in an escaping polar wind flow. And if you just change that percentage, you can get rather different. So this, what are we looking at? This is potential along the field line. So electric potential along the field line. Density of the O+, starting at some value and then watching it go with altitude as you go out, and temperature of the electrons. So the temperature changes dramatically as you add these photoelectrons. Big thing down here is that the photoelectrons are dramatically increasing by orders of magnitude, many orders of magnitude, the amount of the O+ density at the higher altitudes along this field line. This is a quick comparison against Akabono temperatures, showing that for reasonable numbers of the photoelectron density at the start of this field line, you can get temperatures, electron temperatures that match decently well. And now here I'm going to show you two pictures. I'm going to flip back and forth between these. What are we looking at? Again, ion density of O+ and H+ as 2 different style curves on here. The Mach number as these particles are flowing out. Again, bold is O+, light line is H+, and then electron temperature over here. This is for a small amount of photoelectrons. The different curves are for different levels of ponderomotive motive force. This is for a high, 10 times higher photoelectron amount. Low photoelectrons, high photoelectrons. Same ponderomotive motive force being applied. Low photoelectrons, high photoelectrons. Completely different solution when you add in a little bit more photoelectrons. So as you have those extra, depending on whether you're in sunlight or not in sunlight, you can get a dramatically different influence of other effects. It's a transistor on other effects is what I think the point is of these two pictures. So superthermal electrons are important and should be taken into account when we're talking about these global modeling and magnetosphere-ionosphere coupling situations. Thanks.
Questions or comments?
The last two pictures you showed, you went very fast, but
Yeah.
let's look at the H plus
Which one?
on the left. I mean,
Yep.
both of them.
Okay.
So what this was a self-consistent calculation, which means that the photoelectrons pull up the H plus.
Yeah, right. Yeah, so it's, again, going back to this type of slide, it's driving a potential drop along the field line to help pull the particles out. It does not include what Kitamura was talking about earlier in terms of heating down below 500 kilometers of the reflected particles. Right, just the electric field effect. Yeah, so there'd be even a bigger effect if you were heating and changing the temperature down at the lower altitudes. Right.
Yeah, one process that I've always worried about is when you dump, say, an energetic electron from the plasma sheet with energies of maybe a few keV, you produce a lot of secondaries. I mean, you can produce maybe 100 secondaries. So if they all flow out, obviously you have a charge imbalance problem. So how do you actually resolve this problem? And is this actually resolved in George's code?
I don't know if it's a charge imbalance. Well,
we're talking about
a net
relatively
current,
low
though. You can
density
actually have a downward precipitating electron population in a region of downward current because you have more electrons leaving than you do coming down.
I'm not really worried about the current. I'm thinking
if
about
that's what you're pointing at. Okay.
the diffuse auroral precipitation, which is typically a few keV energies. And if you produce you are going to produce an awful lot of secondaries when they hit the atmosphere. How many of them actually can leave the system? Because if too many of them leave, you are going to have a charge imbalance problem.
Yeah, you actually, so I guess that question of, if I'm talking about current is just off of the integration of the electrons flowing downward and flowing upward. I believe that George has come up with the number of 750 as the magic EV number. So 750 EV, if the characteristic energy of the downflowing electrons is lower than 750 EV, then you actually get a net electron flux upward because it produces those secondaries at high altitude. And if it's higher than 750 EV, then the net production is low. They'll be in a region of mostly collisional, and the upward flux is low compared to that down. And so you get Okay. Maybe we can talk more later, but yeah, I'm not sure if I'm answering.
You see, I'm not sure this process is really built into the global models because we lose a lot more electrons than ions as they come in from the plasma sheet.
Yeah, definitely.
The loss times are so much more rapid.
Okay. Yeah, let's keep talking though. Yeah, it's a good point in the global models. I don't know if they include all this.
I'm going to spin off that point a little bit too. I want to reiterate the point that Kitamura made, that when you have really huge ion outflows, it actually depresses the ambipolar potential. And that's expected if the ion flow is large enough to match the electron escape, you don't need an ambipolar potential anymore to hold the electrons back. And you've got huge outflows of both, of course. So I think that points to decreasing importance of the electrons when you have really huge outflows. It's really important for the polar wind and normal sort of conditions, but then it declines a little bit when you, according to those observations.
Good point. Yeah.
Speaking as an observer, I'm shocked that you didn't bring up Richard's paper where he took the fast data and calculated a reflection coefficient as a function of energy observed on fast on the plasmaspheric field lines.
My only defense is that I did not make this talk.
Well, you can share that with George.
And Alex is raising his hand. Okay,
Actually-
Alex will speak to that.
I could do it when I get up there.
Awesome.
It's been a segment.